So this is part 4 today. Subtitle would be Algorithms and Obstructions. We've discussed on Monday Kuratowski theorem. This is a theorem of this type. You want to embed a graph in the plane, and Kuratowski theorem tells you that essentially you can find a subgraph which is either a subdivision of K33 or so if graph is not planar, then you can find a subdivision of K33 or subdivision of K5 as a subgraph. So you find an subgraph homeomorphic to K33 or K5 is the only obstruction to planarity. Now, a word obstruction means that it prevents us to embed the graph in the plane, and by the same time I mean a minimal obstruction. If you delete any point or any edge or anything from such a subdivision, the graph itself, this subdivision, would be embeddable in the plane and would no longer assert that confirm that the graph is not planar. So Kuratowski theorem says that there are only two minimal obstructions. There is a version expressed in graph minors. You can say a same graph is planar even only if it does not contain one of these graphs as a minor. So another formulation of this is K5 or K33 as a minor. Is everybody familiar what a minor is? Maybe not. So let me just give a definition. For a minor, we want basically a subgraph. Let me describe for K5. We want a subgraph in your graph, which can be represented in the following way. You have maybe 5 connected subsets, maybe just a single vertex or something consisting of more than one vertex. And then between these sets, you have all possible edges forming a K5 structure. So this would be 1, this would be here, this one would be here, this one would be here, and so on. So we have, we're missing an edge also from here to here. So this would, a subgraph of this kind would, and maybe you don't need to subdivide edges because you can, if there are more vertices here, you can add them into this connected subgraph. You just, and then you just get single edges. And such a minor also verifies that the graph is not planar, because if this would be embeddable in the plane, you could shrink the edges in these connected graphs and would still get an embedding of K5 or K33. So that's, you see, you can say forbidden as a minor or as a subgraph. It is not true that if you have K5 as a minor, you have K5 as a subdivision in your graph, or vice versa. So For instance, if you take a Peterson's graph, Peterson's graph has K5 as a minor. You just take as your bags, your connected subgraphs, you take this perfect matching, and once you contract them, you'll see each of them is adjacent to each other. So this is K5 as a minor. Of course, you don't have K5 subdivision because no vertex is of degree 4. Now, you may wonder what happens. Oops. So this is about obstructions. Now I mentioned also algorithms, and I should mention that actually a result of this kind gives also polynomial time algorithms for discovering if a graph is planar or not planar. Well, naively, you could just try to find such a subgraph, and if you can do it in polynomial time, you're happy. And it turns out that you can always do such things, and that follows from graph minors theory of Robertson and Seymour. But for planarity itself, even before that theory, there were very, very fast, very efficient algorithms were found. So Lipton and Tarjan in '74, and more or less at the same time, Booth and Lueker. Their paper appeared a little bit later, but it was more or less concurrent discovery. Found two different algorithms that answer in linear time. So this would be linear time planarity testing. If a graph is planar, the algorithm answers in linear time, yes, the graph is planar. And actually, some extensions of this, they were found or published later, even produce an embedding, produce a drawing in the plane. And if it is not planar, it says it's not planar. And again, extensions were found later by other people that would find one of this such subgraph if the graph is not planar, all in linear time. So that's other work. There are many other authors found can also find an embedding in the plane if it exists, or a Kuratowski subgraph, subdivision of one of these. And either way, you find one or the other, you're happy, you have your result, it's easy to verify. Now, question is, what happens with when you go from the plane to more general surfaces? And the simplest surface would be the torus orientable surface, but it's more difficult to deal with than some non-orientable surfaces. Indeed, then Archdeacon found that projective plane has a Kuratowski type theorem. That was proved and classified. The graphs were classified. Instead of these two, you get more graphs by then Archdeacon. In beginning of the 1980s. And he found that same result holds. A graph G is projective planar, so can be drawn in the projective plane if and only if G has none of some family of 103 graphs as a subdivision Now these 103 graphs are minimal obstructions as well, because I'm saying if and only if. So if you just take one of these graphs, I'm saying this graph is projective planar. Well, it's not, if and only if it contains one of this itself, so it must be minimal one. If I remove any edge, it is no longer, if I remove any edge, it is no longer an obstruction. It can be embedded in the projective plane. So instead of 2 graphs, you have 103, and this was actually at the same time forbidden minors were classified. There are 35 forbidden minors. Some of these have edges which you can contract and still not be embeddable in the projective plane. And so you get a smaller list of obstructions. That's now the next question is, does it hold for other surfaces? And this is true. There is a Kuratowski theorem for an arbitrary surface, for any surface. There exists a finite list of obstructions. So for every surface, there is a finite set of graphs which play the role of same role as K33 and K5 play for the plane or the sphere. And as you imagine the numbers, how many of these graphs are, this grows. And it is an interesting fact that besides these two cases, no other surface has a complete list known. So there are many results, for instance, for the torus. Several hundreds of thousands of obstructions are known, but it's not a complete list, so more than 200,000 on less or equal to 12 vertices. And it is not even clear how large can such obstructions for the torus be. So the largest one known has 24 vertices, but and it's probably the largest one. So it's a cubic graph on 24 vertices, which doesn't embed in the torus, but every proper subgraph does. So that's where our knowledge is today. Now, this theorem follows from a more general theorem of Robertson and Seymour, namely Robertson and Seymour theorem proved that for every minor closed family of graphs, for every graph family that is closed undertaking minors. So if you delete any edge, contract any edge, you're still in the family, and then you repeat deleting or contracting any way you like, you keep being in the family. So undertaking minors. That's there exists a finite list of forbidden obstructions. So there exists a finite list F1, F2, up to Fn of graphs that are not in this family. Maybe I should put some name to the family, let's say a script G, that are not in script G. But any graph which is not in script G contains one of these as a minor. any graph G, which is not here, contains one of them as a minor. Now, this is a powerful theorem. It's you've heard about this theory, this sequence of many long papers developing this result. Became famous because it has really striking applications through mathematics and theoretical computer science. A lot of what you heard in these topics, for instance, Dimitrios talks or so, everything came out essentially out of this theory, like the tree width things and so on. Now, one thing to observe is that Robertson-Seymour's proof is non-constructive, so it doesn't give any way to say what n is. You see, graphs on a fixed surface are closed undertaking minors. If you delete an edge, you still have a drawing. If you contract an edge, I explained the other day how that you can really shrink it so that you preserve the embedding. And so it doesn't say anything, so the proof doesn't say anything how big this n would be, or how big these graphs would be. No bound, no constructive bound. So that's a kind of disadvantage. A good advantage is that there is an O of n cubed algorithm. So if you have a graph on n vertices, you can test for each of these if it is a minor in there in cubic time. And since there are only a constant number of them, you just check for each of them, and you'll get testing if your graph is in such a family. So that gives polynomial time, cubic time algorithms for each surface. Of course, you only for this one you know the graphs to deal with. So otherwise, it's not implicit. It's just the existence of an algorithm. Now, this disadvantage was overcome in the 1990s. So I proved in 1996. Well, actually, this was when a stock paper came out, and then the main paper was in the 1999. But there were some supporting results that this result actually needed, so it was actually published only in 2003. I found a more satisfying proof of embeddability results for surfaces. So it's a Kuratowski theorem, and the basic result, let me just state it. So it's the following theorem. For every surface S, there exists a linear time algorithm that, given a graph G, either finds an embedding of G in this surface. So that's one possible outcome. And the other outcome is it finds an obstruction. It finds one of these Kuratowski graphs. Well, one of these, actually a subdivision, or it finds a subgraph homomorphic to a graph on at most, well, let me say just there is some function which is hidden, let's say f of s vertices. This is a number which depends on the genus of the surface. So finds a subdivision of such a graph, and this graph doesn't embed in the surface, which is an obstruction to embeddability in S. So that's the, this is the best you can hope. It's really nice. It's linear time. It's fast. And just to add, there are some darker sides. This linear time has huge constants. So the constants are huge. And the algorithm is complicated. So today, up to today, actually nobody even implemented the torus case for this. So it's just too complicated to be. I had a student who worked on this, on the torus case for a year. He produced around 10,000 lines of a program, but then eventually there were some troubles, so the program was just too complicated, so we never finished. Okay, any questions about this? Yes?
One question, does the Robertson-Seymour also imply that there is a finite list of forbidden subdivisions?
Yes. I didn't say that, but it is true that if you have a finite list of, in a minor closed family, you have finite list of forbidden minors, all you can do is you just take all graphs which contract to these graphs. So basically you uncontract vertices. If you have a vertex of degree maybe 5, you uncontract it in all possible ways. So one way would be this one, for instance. One way would be into 2 vertices. So here you would contract this into a degree 5. So it's, for each graph there are finitely many ways, and the set of these graphs you get will contain all subgraphs. Maybe some of them will no longer be obstructions, but and so it will be finite again for as well. So it's constructive both ways. Yeah.
Perhaps you can also emphasize the dependence on the genus. I mean, this algorithm is linear time for every fixed surface.
Exactly. So this is not disadvantage, because if you want to say, try to find the minimum genus in which my graph embeds. This is called the genus problem. So you can just start with first surface, second surface, and genus of the graph is at most n squared, because you can just use one handle per edge. This would be polynomially many applications of this one. However, it would involve larger and larger genus, and in these constants which occur in the linear time estimates, they grow exponentially, or super exponentially, so it's very fast. And it's known that the genus problem is NP hard, so that's NP complete. So there is no way, no hope to do any better. Oops. So now I will try to say a few words how you can do that. I should mention that this was actually the first proof of Kuratowski theorem, which was constructive. So the last result I mentioned was really the first proof showing Kuratowski theorem and was constructive. So if you follow the proof and you would use right estimates, you would find estimates how big these forbidden graphs would be. I never did that. It's too complicated, but it's explicit in the proofs. Okay, so in doing that, I do a lot about embedding extension problems, and I would like to say a few words about embedding extension problems now. Let me mention a particularly easy problem. So suppose so this is a disk embedding problem. I give you a graph G, and I give you C, which is a cycle in G. And then I ask, is it possible to embed? Is there an embedding of G in a disk containing this cycle on the boundary of the disk, containing C on the boundary? So you draw your cycle C. Well, let me just do the circle. So there are possibly many vertices of C, and you wonder if you can draw the rest of the graph inside. So that's called embedding extension, because I give you an embedding of a subgraph, and I ask, can this embedding be extended to? Now, when dealing with this, well, let me first say what theorem here is. There are different kinds of obstructions for this kind of embeddings. And let me first state just two, which are obtained by some kind of non-planarity. So for instance, you can have your cycle, and then you have maybe an edge here and a K5. So this would be an obstruction. This actually you could it's not an obstruction. You could delete this, and it's still not embeddable. But now it's if you delete any other edge, it's embeddable. So another kind of obstruction would be maybe you have this. Replace one edge by this. So here would be K5 or K33. So this is K5 minus an edge, and then if you add these three edges, you get the subdivision of K5. So this graph certainly doesn't embed in the disk, and it's a minimal obstruction. Now, a theorem which I'm gonna just state is saying basically, if you are tree connected, then basically you don't need these kind of obstructions. So here is a small theorem. If G is tree connected, then GC, so this pair, has an embedding in disk, has a disk embedding, unless one of the following obstructions occurs. Maybe you have a path in a graph joining vertices. So this is the cycle C outside. Joining two vertices A and B on the cycle, so this is a path. And there is another path, which is disjoint from it, and interlaces. So let's say C and D. This is called disjoint crossing paths. Of course, you cannot, if you have this as a subgraph, you cannot draw the rest of the graph in the disk. Some of the edges would need to intersect. And there is another kind of obstruction, which is called a tripod. It's of this kind. It has three vertices. Well, let me draw them just very close to the cycle, and then maybe these three edges. But this could really be just a vertex on the cycle, and then you have two vertices like this, and three paths. So these are, in general, subdivision. So if it contains this as a subdivision. So that's another kind of obstruction theorem. So for this embedding extension, you have essentially, if you're not reconnected, you can have such things in components which are not reconnected to the cycle, but otherwise you can find one of these two obstructions. And you see, it's a small obstruction. Now, here I have another embedding extension problem on an example. So let me do example here. Suppose this is, instead of a cycle now, I give you a graph, which looks like the cylinder here. So I give you a graph on 4 vertices and then these 6 edges, and it's drawn in the cylinder, and this is subgraph of your graph. And you ask if you can embed the rest of the graph inside these 2 faces. So can you draw, there is a rest of the graph. So these are paths, there are maybe many vertices, and there is the rest of the graph attached to this, and you wonder if you can do that. So here I redraw this figure so that it's easier to draw it in this way. I cut here, and then the edge E would be the path on the top, is the same as the path on the bottom. So we identify top and bottom here to obtain this figure. And the rest of the graph are just these edges as I draw them here. So there are some more vertices. Forget this orange coloring for a moment. You see you have F, it's this path, E is this path, and then the rest of the graph is some more edges. Now this cannot be, this embedding of C, so the subgraph C, so this is C, cannot be extended in this case. And you see the reason. This edge must go in this upper face here, because it's attached to this path which is only here on the side, so it must go up there. But then this edge cannot be drawn on this side, so it's forced to go into this part. And then this edge is forced to go into this part, and so on. You see, and then at the end you come to a contradiction. This edge is forced to go here, but then it must cross with this one. So this is a graph which doesn't embed, doesn't extend, and it's a minimal one. If you delete any of these edges, you can embed it. Delete maybe this one, you can flip this second part just around, and it will work. You delete any of the edges, it's a minimal obstruction, and as you imagine, this could be arbitrarily long, right? So what can you do in this case to find a nice obstruction theorem? Well, here is the way to go. We can replace these 2 paths, E and F, with 2 other paths. And then we will find a small obstruction. So let me, here I indicated that I replace E with this orange path, which you can see in the picture, and I will replace F with another path. So I'll do F here. So this is the same part here. So F joins the same 2 vertices, and E joins the same 2 vertices. And now you see what you get here is you get this path here in the rest. So this is the same here. It's just one single subdivided edge. It's just one path, and this is already an obstruction because it starts here, and then it ends here in the other face. So you cannot draw it. With respect to the orange and green subgraph, of course. So here is the message. You can, in some cases, you can, when you do this extension problems, you get obstructions which are minimal obstructions, but they are huge. But in this case, there might be a way possibly to change these obstructions and so that you get something which is much smaller after all. So you get a Kuratowski type subgraph consisting of this single edge, the red edge here, instead of those thousands of them. Now the proof for the surfaces is a longish inductive proof. So sketch of the proof would be the following. So first you try not to embed the graph into the big surface S, but maybe in some simpler surface. Let's try first in the plane, yes?
Do you need the two vertical edges?
So the orange edge, the orange subdivided edge will replace E, will replace this path. The green one will replace F. And now I'm looking at this graph. So it's, of course you need these two edges. This is part of this C. Okay, so I've changed C, I replaced E and F with the orange and green path, right?
As I understand, you fix the boundaries of your surface somehow.
Yeah.
And you have some link to tie the two embeddings. So it seems that you need just one edge and not two. So two cycles just tied by one edge. So that your problem would be meaningful also.
Also, of course, you could have, yeah, sure. Yeah, but this is a general problem. So I give you a subgraph. I will discuss this next. So I give you a subgraph, and then I try to extend this embedding of the subgraph. And this goes as well here. So first try embedding G in simpler surfaces. So that's an induction on the genus of S. Now, if you can embed in simpler surface, it will also go in the bigger surface S. If not, you will find an obstruction. And that obstruction has the property that if you go to a surface one genus more, it has only few embeddings, because the size is bounded by this f of S. By induction, its size is bounded. And now for each embedding, you solve the embedding extension problem. And then you get a bigger obstruction, but it will necessarily go to a bigger surface. And you continue this way. So finding obstructions of, let's call it bounded size. Now this involves a few details. Maybe I should take a minute and prove a small theorem, just to have at least one proof in today's lecture. That what you do is, when you try to extend, you look at the rest of the graph. So you have your obstruction for some surface, and you try to extend it in another surface. So C is maybe now a bigger graph, maybe in the torus. Okay, I've embedded K5 in the torus. So this is K5, what is drawn here. And then I try to extend this embedding. And the rest of the graph I can partition into connected components which are attached to some of these vertices here. So maybe something like that, maybe something like that, and so on. So these are called bridges. This is called a bridge. Bridges could be also just an edge connecting two vertices. So this is your subgraph C was this part. And then you try to see if you can embed bridges in your faces of this graph. Something like here, we try to embed bridges into faces F1 and F2. And then you can get obstructions of this kind or more general, and sometimes you need to change your C in order to make obstructions smaller. So that's the there is one annoying kind of bridges, it's so-called local bridges. So look at this. So suppose you have this subgraph C. So this is C. And then you have a bridge, maybe a vertex or an edge, and then it's only joined to vertices on one subdivided edge. So this I call a local bridge. So these bridges are a bit annoying because in algorithms it is very helpful that you don't have bridges of this kind. So this is another one here. And let me draw a third one. But if your graph is tree-connected, then you can always change your graph C. So here is a little theorem that goes back to Tat. So Tat proved this in the 60s. If G is tree-connected, then C can be replaced by another subgraph C prime, which has these main vertices are the same. Let's say if C is K5, the 5 vertices are the same, only the subdivided edges may change. Like here, so we had these vertices were fixed, and the E and F were replaced by the orange and green path, joining the same pairs of vertices. So that's the change, same as in the examples. So that there are no local bridges after all. So that local bridges disappear. Here is a way of proving this. First of all, you look at this local bridge here and test these two vertices. Well, if since the graph is tree-connected, there must be another bridge which joins one of the vertices inside. This is not separating the graph. To something outside, like this one below. But then if this is local bridge, I extend this to these two vertices. And then again, in this interval, there is some bridge which has a vertex inside interval and outside, like this one. And then I try to look at this interval. And sooner or later, I must come to a point that either exhaust all these local bridges, but I come to a point that there is maybe a vertex here, which is part of a global bridge, which will maybe attach to here. So what can I do in this case? So here is the sketch for the algorithm. Let me just redraw. I just need this bridge, which is covered by. So this was a global bridge going somewhere out, and there was this bridge here. Now what I do is I replace the path by the following. I go to the leftmost attachment of this bridge and then continue here, and then I take a path through here. So this is the change of this path. It keeps the property, the vertices of degree 3 or more are not changed, only these paths change. And it has the property that after doing this, the number of edges of local bridges on this subdivided, on this path E, gets smaller. Why is this? Well, before all these were edges in such a local bridge, but after we do this change, you see this merges into a bridge which is part of a non-local bridge. So you lose some of the edges. Of course, you may get more local bridges here, but the number of edges in all local bridges goes down. And now you just repeat the argument, so after a while all local bridges disappear. That's a simple proof of this fact that you can actually remove. I call this removing local edges. This is an essential part of the algorithms because proofs get very technical, and assuming there are no local bridges, it does help. Now, let me try to formulate a general embedding extension problem. I have a graph G. G is a large graph. And I have a C, which is a subgraph. A small subgraph, maybe one of obstructions for embedding into smaller surfaces. This subgraph comes together with a two-cell embedding in some surface. S. So in general, you can think of this being an obstruction for embedding into surface of genus smaller, and then this would be an embedding. You try to extend it and find an obstruction that will say, oh, this cannot be extended. And then you have to try with maybe another embedding of C, but since C is bounded, you do this just bounded number of times, okay? Constant number of times. So this is true, and then the question is, can you embed the rest of the graph? But we need much more. So we look at all bridges of this subgraph C and classify them into types. Basically saying to which paths, to which subdivided edges in C they are attached according to their attachments. Now, when you try to solve the embedding extension problem, so embedding of C to be extended to embedding of the whole graph, the most annoying bridges are which are attached just to two subdivided paths or to one vertex and subdivided path. And let me just give an example. So maybe C will have such a face, and B will be a bridge which is attached to maybe sigma 1, which is a subdivided path, so it's a path in C, and sigma 2, which is just a branch vertex in C. So if you have a two-cell embedding, and this is a path, sigma 1 can occur on the boundary. So this could be part of this, on this boundary of this face, for instance, like that. Sigma 1. So this is subdivided path in your graph C. It can occur twice, but not more than twice. So this could be sigma 1 repeated. And then sigma 2 is a vertex. Maybe vertex can occur more than once, more than twice, let's say 3 times. And then you have different, so you have a bridge which is attached to some vertices here and attached to this vertex. So they can have different embeddings. Maybe it can be embedded like this, or it can be embedded like this, or a more complicated embedding would be that it is part of the legs go to this occurrence of sigma, and part of them go to this occurrence of sigma, and so on. So maybe there are possibly many different ways, and maybe it also will embed in another phase. Not in this case, because then there is no other phase which has sigma 1 on the boundary, so it cannot be considered for any other phase, but in general it can. And in the embedding extension problem, we have also a kind of, so here is, let me say, a notation. So this, let's say psi would be this embedding, and then tau would be for every bridge type. So bridge is attached to these two, to sigma 1 and sigma 2, for instance, every type of bridges. We have an allowed set of embeddings. Maybe we don't want to allow this kind of embedding, and we don't want to allow this kind of embedding, but allow this one and this one, for instance. So that's data for the embedding extension problem. And so the embedding extension problem, we have given G, C. We also give some vertices of C with 0. V0 is a small vertex set. It's, let's say, it's of cardinality at most k, where k is some parameter. And V0 contains, in particular, all vertices of C of degree different from 2, and maybe some vertices of degree 2 as well. So that's possible too. So V0 is a subset of C, of the vertices of C. And then we have the two psi and tau. So this is the data, and the question is, can I extend this embedding psi of this graph, of this subgraph, to add all the bridges, all the rest of the graph in some phases, so that I don't create any crossings. So that's the embedding extension problem. It looks general, but this is a way which is actually needed, because how the algorithm works, it tries to find an obstruction first for very simple ways. Maybe try to only use this kind of embedding for these bridges, and then if you find such an obstruction, you get a little bit bigger C, and then you work with that bigger C and try to find an obstruction to allow this type and this type of embeddings and so on. So this goes in a way of a kind of obvious, more and more complicated ways of embeddings. There is another kind of induction in there, which I don't have time to mention, but let me just mention the main result about this embedding extension problem. So that's a theorem which enables the main result. And I'm mentioning it because there is an increased interest in this. So well, maybe I will comment this at the end. So given there is a function f, it will depend on this k, such that every embedding extension problem, GC V0 psi tau, with V0 containing only the bounded number of vertices, at most k vertices, either an extension exists, of the embedding of psi, an extension of psi to G exists, using only this allowed types of embeddings. And this can be found in linear time, let's say O of n. There is, of course, these constants depend on k. Or B, one can find a small obstruction. So C can be replaced by a C prime. Now, when you replace C and C with C prime, you consider a same rotation system. So you consider basically the embedding, which is the same as psi, but it uses different edges. So let me call it psi prime, and the same types. And there are at most this many, not too many, only bounded number, f of k, additional vertices and paths added to C prime. So we add a few more vertices and paths, like this disjoint crossing paths or tripods for the disk embedding, so that this forms an obstruction. So that this subgraph, which is just of constant size, doesn't have an extension of the required type. And so this then inductively, so add it to C prime, such that we obtain an obstruction to embedding this subgraph, to extending the embedding of C prime as requested. So that's the main theorem, and complicated induction then proves the main thing. Now I mentioned I decided to present this result. This is almost 20 years old result now. Why would I talk about that right now? Well, it is actually not many people are familiar with the details about that, and moreover, there is a growing interest in this. So it's a recent isomorphism testing for graphs of bounded genus uses this kind of algorithms, the embedding extension. So you try to decide if two graphs are isomorphic. This is a well-known problem with unknown, undecided complexity. And for graphs of bounded genus, you can use this to find a very efficient linear time algorithm for that for the isomorphism. And there are other things where this occurs as you would hope for. Okay, I think I'm over my time, but maybe a short question could be. Any questions about this?
It seems not. So thank you very much.
Okay.